Okay, let's look at a diagram of what it means. What does the gradient do? So we have this gradient, this little triangle thing. Okay, this triangle thing was the del. Operating on a scalar function, we call it a gradient. What does it actually do? If you look at, let's say, a surface, a curved surface. Okay, let's say you have an xy plane, and we'll take this is xy, and we'll take v of x, potential as a function of those points in x, will be some function, which is the surface. Okay? If we look at the valleys and mountains and so on, wherever you are, like if you climb the hill or the mountain, and you're going down, you look usually for the least steep way to go down, right? Unless you want a little adventure. So if you go in this direction, maybe it's kind of like this. If you go in this direction, maybe it's very steep. In this direction, it's sloping, right? So you might choose to go, or if you want to adventure, you'll choose the steepest way. But from any point, there's usually several different paths that you can take. And once you get here, to the next point, there's also several different ways that you can go. There's, in the functions like this, there'll be one steepest way. All right? The steepest way is the direction of the gradient vector. Okay? So that's why you have the word gradient in English also. It means like the difference between things and so on, but the more technical meaning would be the steepest difference between. So you can also think of a potential as being determined by contour lines. You know, like you have on a map, the height will be given by contour lines. The lines tell you, in other words, equal height. Each line, each circle is an equipotential. In other words, an equal height of the mountain. The next height is given by this line. Now, it's not circles. If it was a perfect like cone like that, it would be exact circles. Right? But the mountain is not like that. The mountain is, here it's higher and here lower and so on. Okay, if you have two adjacent lines like this, right, let me make them 3, you can have something like this in a contour map. Right? It means all of these points have the same height, all of these points have the same height. Now you can see that from here to here is very steep, because this is the next height reference point. And you only have to go a very short distance to get to that height point. Whereas if you go from here to here, let's say, you're crossing the same height differential, but through a much longer path. So clearly this is less steep than this. So the lines that are closer together means it's steepest. So the gradient would be, let's say, here. From this point would be here. From this point, the gradient might be, let's say, here. You know where it's highest, where the mountain is tallest, or steepest actually, not tallest?
Steepest where they're closest together.
Where the lines are closest together, that tells you it's steepest. Here it's steeper and here it's less steep, so the lines here will be closer together than here. All right, so you can have a map, contour map, where the lines have different closeness and right distance from each other. The gradient, the steepest descent, will be when the lines are closest. All right, so the shortest line connecting. So the gradient gives you a definite directionality. Conversely, if you have a vector field, at every point there's a vector in some direction. Certain kind of vector fields can be mapped by giving you the scalar function, where the function is built exactly so that the steepest point from that, the steepest direction from that point, points in the direction of the vector. So instead of having a bunch of vectors, what you have is a surface. From that surface, you can derive all the information that you need to construct the vector. Because given that surface, you simply measure what's the steepest descent, point the vector, so to speak, in that way, and that gives you the vector at that point. And go to the next point, figure out from here now, what is the steepest way, or the opposite, it could be plus or minus of the gradient, right? And that's exactly the property of A. A has that property, that it can be constructed from a surface like this. And it's called a potential, a gravitational potential. You can have electrical potential, okay? In other things you have potential. What does this mean? We now know enough to say so fields which have zero curl have this property. What does it mean to have a curl? If you look at, let's say, this diagram, you have vectors of equal length going around in circles. Okay? What this means is as you go along here, the field remains the same strength, just as changing direction constantly like this. How would you represent this with a surface in gradient? In order to do it, what would have to happen at each point? What would have to be on the surface? The steepest descent would point to in the direction of this vector, so to speak, right? But what happens if you go around a complete circle? The steepest direction goes, let's say you have a mountain.
Comes around to itself. So
Comes around to itself, so the steepest direction, exactly, the steepest direction is pointing this direction, and the steepest direction pointing the, it's like, as he says, it's like the Escher drawing when you're going up and up and up and up and up and come back to the same point. You can't go around in a whole circle where you're constantly going in the steepest way and you come back to the same height.
You're flat or something.
Right. So that's what it means that there's a curl. This has a curl. This vector field has a curl. Zero curl means that you can,
It's physically.
and in a zero curl, you can define this function such that you can consistently give the slope the greatest slope, and that maps onto the vector. Okay? So it has, it's a curlless.
So curl is like when it has like exactly the same height. I mean, if you go around the circle, it doesn't change at all, doesn't move up or down. Or
Right, right. But you wouldn't be able to consistently say that that's the steepest. There would be no meaning to say that it's the steepest.
Like if you start at one point, you keep going the steepest way, and suddenly you're back on
You're back in the
yourself.
same place. It
It's
can't
not
be.
possible. You can't go like down, down,
You
down.
can't go down in the steepest way,
And then-
down in the steepest way, down in the steepest way, and come back to the same thing.
so this is what the curl is, right?
Like in a field with a curl,
Yeah.
it's impossible to make this mapping of surface with steepest mapping onto the field, because you'll get to this paradox. It's about, but in a field where there's no curl, right, you can do it. Right? You can always find some surface where if you go in the gradient, you'll end up mapping exactly the vector field.
So curl is basically like a circle, right?
Something circular, right? And in fact, in English, curl, that's the same kind of word, it curls around. Okay? And you can see examples in vector calculus books of fields that have curl, that don't have curl, and so on and so forth.
So,
Okay.
So when curl is equals to 0, then it doesn't have any on it. So when curl...
When the curl is equal to 0,
Yeah.
then this piece, the second piece vanishes, and all that's left is the gradient of f, which means automatically there is some function f that you can find such that the vector field can be given as its gradient.
Right.
Okay? So we know from when we see div a is equal to rho, if you tell me this entirely specifies the acceleration, I know right away that a is the gradient of phi. Otherwise, this would not specify. Okay? So this is my field equation. There's also, when you have a potential, you can define an energy. What does the energy conservation come from? It comes from the fact that no matter which path you go through, there's this quantity which you can call the energy, which is a combination of kinetic energy and potential energy, which remains constant. It's path independent. If I pick this chalk up and I move it like this and like this and move it to here, or if I pick it up and move it like this and like this and like this and like that to here, the energy at this point is the same as it didn't matter what I did to it to get here. The potential plus kinetic energy is the same. All right? It doesn't depend on the history. It doesn't depend on the path. In some certain kind of fields, it might. Because in some fields, maybe it depends on the velocity of your particle. Maybe the field is changing with time, so this one took longer than this one. It was affected by some variation. All kinds of things can cause it not to, right? And there could be a curl. There are all kinds of things that cause it not to happen. When you have this kind of thing with a gradient, you can find this path-independent quantity. So that's another thing. That's what's nice in Newtonian gravity about the fact that there's a potential. That you can define this quantity called the energy, which is path-independent. It doesn't matter how you get from one to the other. Okay? And this we've seen many times, of course, right? The line integral over a path. Two reasons. One, because in ordinary gravity theory, when you taught it in your first course, the potential is kind of like, what's the importance of it? What do we have as the potential? You're told the acceleration is gm over r squared, right? If it's a vector, then you have r hat over here. And that is equal to the gradient of the potential. With maybe, let's say, v. All right? And what is v? V is basically 1 over r. Gm over 1 over r. Big deal. I mean, the derivative of 1 over r is 1 over r squared with the sign change. So what? Big deal, right? what's it? So it turns out you can do all kinds of tricks, energy calculations and stuff like that. It's very nice, but it doesn't have a real significance. The significance is geometrical over here in terms of the vector calculus. And we'll now go see some more geometrical significance of it. So now we can see in a very nice, like, vector calculus way what it means that A is the gradient of a phi. What does it mean, the gradient? This is a scalar field. Have a source, have a bunch of points of space outside. There's a field defined, a potential, which is just a scalar, a number, right? A number at each point in space, meaning a function. We look for the gradient. We see how does that function change. We're standing on a point out here, and we look, where is the steepest change? And we draw an arrow in that direction. It's minus the gradient, we draw the arrow this way, let's say. Right? And we can fill space, instead of with points, which is a scalar field, we can fill it with arrows. Right? Given the values, we simply find where's the steepest descent. Put the arrows, we have now space filled with arrows, which means we have a vector field. That's the acceleration. And it's always going to point this way for a spherical source. In ordinary gravity theory, when you taught it in your first course, the potential is like kind of like, what's the importance of it? What do we have as the potential? You're told the acceleration is gm over r squared, right? If it's a vector, then it's, you have r hat over here. And that is equal to the gradient of the potential. But maybe let's say v, all right? And what is v? V is basically 1 over r, gm over 1 over r. Big deal. I mean, the derivative of 1 over r is 1 over r squared with the sign change. So what? Big deal, right? You know, what's it? So it turns out you can do all kinds of tricks, energy calculations and stuff like that. It's very nice, but it doesn't have a real significance. The significance is geometrical over here in terms of the vector calculus. And we'll now go see some more geometrical significance of it. Okay? Let's look at a diagram of what it means. What does the gradient do? Now, we're going to look at this a little bit more, a little deeper. We see that this gradient thing has to do with a special path. It has to do with the shortest distance between contour lines, right? There's also, when you have a potential, you can define an energy. What does the energy conservation come from? It comes from the fact that no matter which path you go through, there's this quantity which you can call the energy, which is a combination of kinetic energy and potential energy, which remains constant. It's path independent. If I pick this chalk up and I move it like this and like this and move it to here, or if I pick it up and move it like this and like this and like this and like that to here, the energy at this point is the same as didn't matter what I did to it to get here. The potential plus kinetic energy is the same. All right? It doesn't depend on the history. It doesn't depend on the path. In some certain kind of fields, it might. Because in some fields, maybe it depends on the velocity of your particle. Maybe the field is changing with time, so this one took longer than this one. It was affected by some variation. All kinds of things can cause it not to, right? And there could be a curl. There are all kinds of things that cause it not to happen. When you have this kind of thing with a gradient, you can find this path-independent quantity. So that's another thing. That's what's nice in Newtonian gravity about the fact that there's a potential. That you can define this quantity called the energy, which is path-independent. It doesn't matter how you get from one to the other. Okay? And this you've seen many times, of course, right? The line integral over a path. But it's a quantity that doesn't depend. It depends on the 2 points. It depends on the endpoints. Like when you do the integral of a path integral, like f dot dr, right, to get the potential. You have an endpoint, 2 endpoints, 1 and 2. This quantity, the energy, will not depend on the path. It depends only on the endpoints. You'll get an integral, you just plug in this endpoint minus that endpoint, and that gives you the quantity. It has something to do with the endpoints. It doesn't have to do with paths between